Today we are going to see the rotational motion. Then analog between rotational motion and translational motion. First we will see analog between these two. That means different physical and quantities used as in linear motion or translation motion and in rotational motion. Here suppose we have studied linear motion or translational motion, linear displacement, then linear velocity, then linear acceleration, then force, then mass, then linear momentum, suppose this linear displacement shown by S, linear velocity shown by V, linear acceleration shown by alpha, force shown by capital F, mass shown by small m or capital M, and linear momentum we consider P be the linear momentum. Now the analog quantities for all these in rotational motion, linear displacement we direct give analog, that is linear displacement with angular displacement, linear velocity with angular velocity, linear acceleration with angular acceleration, force is replaced by torque, mass is replaced by moment of inertia, and linear momentum by angular momentum. Angular displacement denoted by theta, angular velocity denoted by omega, angular acceleration denoted by alpha, torque by tau, moment of inertia by capital I, and angular momentum by capital L. This is analog between linear motion and rotational motion, or we consider in between rotational motion and translational motion. This is all about analog. Now we will consider next one, that is axis of rotation. Suppose we consider any body rotates. Suppose we consider any type of body. Suppose this is the body of any shape. Then suppose we consider this body is in rotational motion along this line. Then all particles, suppose this is first particle, second particle, third particle, fourth particle, then all these particles rotates in circles. But some particles does not rotates in circles. They spins only. And if we consider locus of all these particles which spins, not rotates in circles, then if we consider all these particles lies on the line, straight line, and this line we call it as a axis of rotation. Locus of all particles which does not rotate in circles but they spins only, and all these particles are on the line, one straight line, and this straight line we call, in case of rotational motion, we call it as a axis of rotation. Now we consider another one, moment of inertia and radius of gyration. Moment of inertia and radius of gyration. See here. Suppose we consider body of any shape, and suppose we consider this is the axis of rotation. Along this axis this body rotates like this, suppose like this, omega. Now we consider suppose different particles. Suppose this is first particle having mass m1, this is second particle having mass m2, this is third particle having mass m3, this is fourth particle having mass m4, This is nth particle having mass mn. Suppose these are the distances r1, r2, r3, rn, r4. These are the distances of all particles from axis of rotation. Now, this moment of inertia, if we consider the translational motion, straight line motion, then in that type of motion, there is a tendency of body to maintain its state. That means to maintain its state of rest or state of motion, and that quantity in linear motion we call it as a inertia. But in case of rotational motion, again there is a tendency to maintain its state of rotation or state of rest, and we call it as a moment of inertia. And we will define this moment of inertia. Suppose I be the moment of inertia, then it is nothing. We can write here mathematically as I equal to m1 r1 square plus m2 r2 square plus up to mn rn square, or I is equal to, we write symbolically, mathematically, I equal to 1 to n summation I equal to 1 to n mi ri square. This is the moment of inertia. And how will we define in words? Moment of inertia of a body about a given axis of rotation is sum of product of mass of each particle and square of its distance from the axis of rotation. This is moment of inertia. And from this mathematical formula, we can write unit. This moment of inertia is measured in kg. M is measured in kg and r is distance in meter square. Kg meter square, or we write here gram centimeter square. And dimensions like this: m1 mass one time, L2 and T0. This is the dimensions of moment of inertia. Now we will consider, suppose a uniform distribution of body is rigid body, then this also can be written like this: I is equal to integration x square dm or r square dm or y square dm, like that. This is all about moment of inertia. Now we will see the physical significance of moment of inertia. Physical significance of mi, moment of inertia. Suppose in case of translational motion, we write force is equal to mass into acceleration. And in case of rotational motion, we write here torque is equal to moment of inertia mi into angular acceleration. Here see, force analogous with torque, linear acceleration analogous with angular acceleration, and therefore mass is analogous with moment of inertia. Therefore we can say that is moment of inertia is nothing but mass in rotational motion. This is the physical significance of moment of inertia. This is all about moment of inertia. Now we will see radius of gyration. The radius of gyration of a body about a given axis of rotation is, it is the distance between the axis of rotation and the point at which whole mass of the body is supposed to be concentrated so as to possess the same moment of inertia as that of the body. Suppose this is the body of mass m, and suppose I be the moment of inertia of this whole body. Now we will replace this body. Suppose I will write here I is equal to summation mi ri square, I equal to 1 to n. This is the definition. Suppose we consider axis of rotation is there, same axis of rotation, and suppose we consider same mass of body is placed here, same mass as that of the body, and suppose this k is the distance of that mass from axis of rotation, then moment of inertia of this body I will write I is equal to mk square. Then if this m and moment of inertia body is same, then that distance k we call it as a radius of gyration. That means it is the distance of a body. It is the distance from axis of rotation of a point mass having same mass as that of the body and possessing same moment of inertia as that of the body, and that distance we call it as a radius of gyration. This k is radius of gyration. We can write k is equal to root I upon m. And physical significance of this radius of gyration, physical significance of radius of gyration, physical significance of radius of gyration. That means radius of gyration depends upon, first thing, position and direction of axis of rotation. If direction and position changes, then radius of gyration changes. Second one, distribution of mass. If mass distribution changes, then again radius of gyration changes. And third one, shape of the body. If shape of the body changes, then again radius of gyration changes. And here we consider unit of radius of gyration. It is the distance, say for meter or centimeter. This is the unit. And dimensions are m0, L1, T0. This is the dimensions of radius of gyration. This is all about moment of inertia and radius of gyration.